present, and prospects, I can read for sure, of game AI. Let's go ahead and welcome Jonathan.
Thank you very much, Matthew. Thank you for the opportunity to be here. I was at the first AIIDE. I actually gave the only keynote at the first AIIDE in 2005. I don't think anybody else was here in 2005, but it was a great lecture. And in 2006, I was the conference chair. In 2007, the program chair. And I went to probably the first 10 to 12 AIIDE conferences, so I have a long history. And then university administration sort of corrupted my life, and it's nice to be back, so thank you. I have not been doing game AI research or very much in it in the last few years, so I don't feel qualified to give a deep technical talk about game AI. But I've been doing this scarily for slightly over 50 years, and that's actually pretty impressive given that I'm 49 years old. But I thought I would give a talk on just rather unusual and personal. So in part, this is a history lesson because I witnessed and participated in some of the history, so I have firsthand knowledge. In part, it's personal experiences and those relating to the University of Alberta because I've been privileged to be part of a team that we built here at the university that has done some fantastic work, not only in AI, but in particular in game AI. And things that are more personal and University of Alberta related, you'll notice will be in blue text. And then I'm also going to, in part, make observations on AI and game AI and lessons learned. And some of those lessons, I hope, will resonate with people here because I don't want you to make some of the mistakes that I made. And those comments will all be in red. So it's a multicolored presentation. And the theme I'm going to use is chess, because when I started out, chess was a very big topic in AI. And today it's an almost irrelevant topic in AI and thereby hangs a tail. And so most of you probably have never written a chess program or even are interested in chess. But I think it's important to understand it from the history point of view. And I'll also mention other games and other activities in a more general context. Why was chess so important? It was supposed to be what was called the Drosophila of AI. The Drosophila is the fruit fly, the idea that it was an experimental domain that you could explore artificial intelligence ideas in a very simple, well-contained sandbox, the chessboard, and learn about AI in this domain and then extrapolate it to real-world problems. And it was an early dream of the pioneers, as I'll talk about, to build a world-class chess-playing computer. And when you go back and look at the literature, in particular in the late 1950s when the Dartmouth conference in AI was held, which is sort of like the start of this long AI revolution that we're in right now. The point was to build one of the foundational problems, the grand challenge problem was to build a world-class chess or checkers and ultimately Go playing program. And the literature just says this was going to be easy. And it was supposed to be so easy until reality stepped in. And this is Herbert Simon, who is an amazing, amazing man. He started out in economics and then switched to psychology and then switched to computing science. And in computing science, he won the Turing Award, which is the Nobel Prize of Computing Science. And in psychology, he won I don't even remember the name, the most impressive award that you can win for psychology-related research. And for his work in economics, he won the Nobel Prize. So here's a guy who mastered 3 separate disciplines. And he developed one of the first chess programs. And in 1957, he wrote that within 10 years, a digital computer will be the world's chess champion unless the rules bar it from competition. And so I want to point out the first thing that's a lesson, if you will. Make AI predictions at your peril. I have made predictions. I will not repeat them here because they will be extremely embarrassing to me. I've made predictions in the stock market, and I won't discuss them here, but they have been extremely embarrassing to me, which is also why I needed 50 years at a university before I could retire. So make predictions at your peril, and especially today, anything to do with AGI, pass it on to some other fool who is going to open their mouth and say something stupid, and let them be quoted and face the consequences. And having just said make predictions at your peril, I'm going to break my own rule, and I predict that you're going to ignore me and you're going to make those stupid predictions. Good luck with that. Okay, let's go back and talk about a few things from some of the lessons that have come out. This is from Baron Wolfgang von Kempelen, who, as a challenge, built a machine that would impress the Empress of Austria. And he built this chess-playing machine, which was called the Turk, and what would happen is that this machine would play chess moves, and it was quite a strong player. Now, we're talking about 1770, so everybody in this room knows there really was no computer there. But what he did was build a very clever machine with hidden compartments, and inside the machine was a very small human who could play strong chess. And this was an amazing accomplishment in 1770 and resulted in numerous journal papers as people tried to understand how this machine could play chess. And it was great because he fooled everybody. There was a crank on the side so you'd wind a spring and wheels would go around, and it looked realistic. And this program, or this machine, or this thing, played Napoleon Bonaparte and beat him. It played Benjamin Franklin and beat him. So, I mean, this really astounded people. And there's a lesson there, which is still being repeated today, is that with AI, you can fool most of the people some of the time. And people were fooled, and they thought it was a machine. And of course, it wasn't. It was all an illusion. And my mantra today is that AI creates the illusion of intelligence, because I have yet to see what I consider intelligence out of computers. I see algorithms that do strange things, and as we'll talk about at the end, these strange things are unhuman-like, but nobody cares, because what goes on in AI is the result that counts. Nobody cares how you get that result. We can talk about how LLMs work, but is that really intelligent? I would argue not. But nobody cares because the performance is generally impressive, and that's all that people care about. The result, not how you get the result. Scientists care about how you get the result, so we're different. Here's a machine from 1912 built by Spaniard Leonardo Torre de Cuevo, and it just played king and rook versus king endgames, chess endgames. And this is the first functioning AI hardware. I mean, this is a century, almost a century ahead of the field, in that he built a physical machine that would do something that humans considered intelligent. Only humans could play chess endgames, and this machine could. And there are many books that consider this to be the first computer game, because it is a game and it is playing it, and it's being done by electronic circuits, not software, but all hardware. Moving forward, here's a picture of Claude Shannon, and Claude Shannon may not be a household name to you, but he is the father of information theory. A lot of what's going on today in the internet was is based on technology that Shannon developed in the 40s and 50s. And amazing man. And he was interested in games and puzzles, and he built a chess machine. And here he is demonstrating it to Edward Lasker, a chess master. Shannon is on my right-hand side. He's the one with the tie. Absolutely a brilliant man. And he wrote a seminal paper, a thought exercise. How would you build a chess program? And he was the first to articulate this interesting trade-off between search and knowledge. And he presented two approaches to how you could solve or build a chess program. One was doing deep searching with relatively little knowledge versus what he believed the humans did, which is using lots of knowledge and relatively little search. And when you read that paper, it stands up incredibly well today. I mean, this is the year 2025. It's over 75 years ago he wrote it, and it was really incredibly insightful, and basically gave a template for how to do artificial intelligence, the extremes, trade-offs between lots of search and little knowledge, or lots of knowledge and little search, and hybrids in between. And here's personal. There's Claude Shannon. He's here in Edmonton at a fellow named Tony Marsland's house, about a kilometer or two south of here at the time. We held the World Computer Chess Championships here, and Shannon was invited to dinner, and we're there. And he was a game person and a puzzle person and a juggler. And we're making dinner, and spur of the moment, he reaches into the bowl and pulls out all the potatoes and starts juggling them to demonstrate that he can, and then took those potatoes and put them into the boiling pot of water, and we ate those man-handled potatoes. So in some sense, I've digested Shannon's fingerprints. I don't know if they've had a genetic impact on me, good or bad, but anyway. The first computer chess game was 1952. This is a picture of Alan Turing, and here's a copy of the document that he wrote, including with his correction, describing how he would do this chess program. And he basically wrote out an algorithm for an evaluation function for his program. And he was unable to get the program programmed because he didn't have enough access to resources for programming this on a 1952 computer. We're not talking about using Java to write this code. This was all machine language code that had to be done, and he just didn't have the resources. So he hand simulated. He played a game against a human, and he pretended to be the computer and simulated how it would play. So in some sense, that was the first computer software game where he wrote the algorithm and he was the software, if you will. But his work, foundational work on artificial intelligence, inspired him for what was called the imitation game, or now the Turing test, as how do you assess artificial intelligence? And this all came back from his passion and interest in chess. In the 1960s, we graduated to novice programs. The first real functioning competitive chess program was written by Richard Greenblatt at MIT, called Mac Hack 6. And you can see a picture of it playing in a human tournament in, this was 67. And you'll notice beside the chessboard is a telephone, because there was no internet then. The moves were computed at the MIT lab, and then he would pick up a phone and dial it to where the chess tournament was and relay the move, and this is how it was played back and forth. And the program played legal chess and actually acquitted itself quite well in those days, and it was certainly quite a novelty. Now let's get on to the real serious stuff for computer chess, which happened in 1970. And the first computer chess competition was held. It was part of what essentially became the ACM, the Association for Computing Machinery's annual conference, and it was held as a one-off event to see if it could spur interest. And here you can see the awards presentation at that first event. Let's see, my cursor shows up. Good. Here is Monty Newborn, who was then at Columbia University, soon went to McGill University, and he was the co-organizer of the event. These two people here are David Slate and Larry Atkin, who were the programmers of, I call it the Chess X.Y program because every year they changed the number. This first time it was like 3.0, and then there were various other variants, and so it's just easier to call it Chess X.Y. And this is the competition result where the Northwestern program won in 1970. I'd like to call this the longest running experiment in computing science history. It started in 1970. There have been computer chess tournaments every year since then. I organized the one last year in Spain. It was the 50th anniversary of the World Computer Chess Championship, which was the first one was in 1974. So this competition has been going on for 54 years. There was one this summer. So there's 55 years now. And you'll see some of the results in a graph I have at the end. But it's amazing to see that computer chess programs have been benchmarked annually for over 50 years. That's quite an accomplishment. From the University of Alberta, the other thing here is these 1970 competitions were the first in computer science history. Competitions that encouraged people to come, in this case, physically together, compete, exchange ideas, and come back the next year with a better program. And it spurred on competition. In fact, the growth in the abilities, the strength of these chess programs took off after 1970 because you got a critical mass of people together talking, freely exchanging ideas, and people wanting to take those ideas and do better for the following year. And of course, in computing science today, this is commonplace. There's lots of competitions. But the first one is 1970. And this is a major historic result that's often overlooked. It started in computer chess. And one thing I'd like to point out for the University of Alberta connection is Tony Marsland had just left Bell Labs, and he was driving across the country from New Jersey to University of Alberta to take up a faculty position. The tournament was the last week of August, and that's when he was driving because he started at the university September 1st, 1970. His program competed and unfortunately finished last. All right. I mentioned already there was a World Computer Chess Championship, so it wasn't enough to have annual tournaments, which were initially just for North America. In 1974, created a World Championship for International to bring the best programs in the world together and compete. This is a picture of Mikhail Donskoy from the Soviet Union back then with a program called Kaisa, which won the World Championship. And again, you can see he's on the phone because no internet, use expensive phone calls. This competition had an unexpected side effect. The organizers did not appreciate that many of these programs needed to have phone calls, and chess games were often 4 or 5 hours long distance, around the world, times 4 rounds, times a dozen or more programs. When it was all said and done, the organizers were very happy until the phone bill came in. Too bad. I just want to put a footnote here, just as a personal note. But I was playing chess back then as a student, and I was the Ontario junior champion of under 20 years old. And I qualified for the Canadian Junior Championship, and in June of 1974. I played in the Canadian Junior Championship, which was in Toronto. And there was a competitor from Alberta here, from Edmonton. His name was Murray Campbell. So I met this guy named Murray Campbell in 1974, and we met and we had a good time and liked each other. And then I didn't see him for a long time, and I'll tell you a little bit more about Murray if you don't know who he is. Now, I was an undergraduate student at the University of Toronto in 1977, and I just was amazed. I was in computing science, and I was playing chess, but I hadn't really thought about it. But I was amazed to find out that literally 3 or 4 blocks away from me, the World Computer Chess Championship, the second one, 1977, was going to be played, and it was going to be played in Toronto. And I could just walk to it. Wow, that's fantastic. And all the best programs in the world were there. And picture here of former world chess champion Mikhail Botvinnik. He was going to be there, guest commentator. And I was there watching what turned out to be the most famous game in the early days of computer chess. And this is the position, and you don't need to be a chess player to understand what I'm saying, but white was a program from Duke University called Duchess, Duke University Chess. And he's playing Kaisa, who won the 1974 World Championship. So Kaisa was the defending world champion. And in this position here, and I'm in the audience, actually not in the audience, I'm standing at the back because like all these esteemed people and all these other media people and whatever are there. And I'm just like this lowly undergraduate student who wouldn't dare take a seat away from some adult. So I'm standing at the back of the room watching. And I know chess, I'm a master player at the time. And in this position here, again, you don't need to know chess much. Kaisa is in check. Duchess has moved its queen here. It's attacking the black king. The obvious move is king goes from g8 here up to here to g7 to get out of check. But Kaisa played this rook here. And the moment it played it, the audience broke out in laughter. Because of course, it's now Duchess's move, and Duchess just goes, queen takes rook. You're down a rook, you're lost. Kaisa resigned, game over. And the commentator, international master David Levy, was there, and he's just ridiculing, oh, this is so stupid. Come on, these computers can't play. You know, it's just pathetic. And even the world champion, because I looked at him, you know, the world chess champion, one of the greatest players of all time, he's in the front row, and he's laughing along with all of us. And the commentators are just saying all these rude and ridiculous things, and it just to rile up the audience, and it's funny, okay, how bad these programs play. Until you discover that in this position here, yes, black makes this move and loses a rook. But had black played the obvious move to move the king out of check, white has a forced checkmate. And the computer saw that and knew it. But nobody in the audience, not me as a master, not world champion, former world champion Botvinnik, or any of the other strong chess players in the room noticed it until after. And this is the first example of hallucinations. These chess programs would do things for reasons we didn't understand, and sometimes they were right, as in this case, and sometimes they were wrong. And when they were right, people said, oh, they just got lucky, and when they were wrong, the programs were ridiculed. And over the years, I was at many computer chess competitions, or actually computer game competitions, not just chess, where when the computers made what people thought was this bad move, they would just be completely ridiculed. So also in 1977, after this tournament, which was in the summer, I think August of 1977, in September of 77, as a student, I walked through the University of Toronto bookstore, and I saw this book on the shelf called Computer Chess, and I said, I'm going to write a chess program. So I bought my first computer chess book in 1977, and you can see it's written by Monty Newborn, who you saw in the picture in 1970 at the first computer chess tournament. And I used that book as an inspiration, and 4 years later, I was playing in computer chess competitions. Now, in the 1970s and early 1980s, computer chess was dominated by this the program chessx.y from Northwestern. David Slate and Larry Atkin. This is Larry Atkin. There's David Slate. Did the program. And they did what everybody did at that time, and I thought I needed to do at that time, which is to write a program that was knowledge-based, and they just were frustrated trying to hard code knowledge. And so they put in a program that did a lot of search and used very little knowledge. And again, they were ridiculed as something called brute force search, which was synonymous with stupid search. And yet, this program had phenomenal success. And the more people looked at doing the simplicity of search, because search is just an algorithm, or it's a recursive, in their case, is a recursive depth first search. It's easy to program recursive depth first search, but to program chess knowledge, hard coding in rules, what's a pawn worth, what's a king worth, how is a king safe, was really hard. And they got rid of the complexity and replaced it with search. And this notion that search is knowledge, and the two are equivalent in some sense, was deep and profound, and took many, many years before people realized that deep brute force search is actually an extremely powerful technology. Here's a lesson that any publicity is good publicity. I've already introduced you to Tony Marsland. There he is on the right. He actually lives on Vancouver Island. I saw him about 3 weeks ago. He looks almost the same. Here's a picture from the 1980, the World Computer Chess Championships, the third. There's Monty Newborn, who wrote the first book of mine that I read. There's Tony Marsland. There's David Slate of chessx.y fame. There's David Levy, who for many years was a computer chess commentator and made some famous bets against the computer programs. There's Claude Shannon and his wife. This fellow I'll talk about in another slide. His name's Ken Thompson. This is Tom Truscott, an internet and Unix pioneer. He's the one who wrote the Duchess chess program that beat Kaisa. I say any publicity is good publicity. As I told you, Tony in 1970 was driving to Alberta to start his academic job. His program was playing in New York City at the first computer chess championship, and it made a really bad move and lost. New York Times happened to be there watching, and the next day he appeared on the front page of the New York Times with "Computer loses in king-size blunder." Too bad. But a few years later, there was a computer chess tournament in North America, and Kathy Spracklin, who was one of the pioneers, she and her husband Dan Spracklin wrote a mini chess program, Sargon, if anybody knows. It's just running like on an 8-bit. Maybe it was even a 16-bit at that time microprocessor. Tony Marsland was in the competition running on this, multi-million-dollar mainframe. Anyway, Kathy Spracklin's flying to New York to come there for the tournament, and she's sitting on the plane, and she takes up a chat with the woman beside her, and it turns out that they talk back and forth, and this woman was really fascinated by chess programs, and she said, gee, my husband would be really interested. I'm going to get him to come to the tournament the next day. And so the next day, Kathy shows up at the tournament, and they're competing, and they happen to play Tony Marsland, and their program running on this, cheap little microprocessor beats this multi-million-dollar computer, and that story ends up on the front page of the Washington Post, because it turns out that that woman who was sitting beside Kathy Spracklin, her husband's name was Bob Woodward, who is the Woodward in Woodward and Bernstein, who uncovered the Watergate scandal and wrote the famous book and the famous movie about Deep Throat. And so he was a famous journalist at the time. He showed up he sat there front row and center, watched the debacle, and wrote the article. Um, uh, anyway, when I had some media success in the 1990s with my checkers program, I was told, thank you for doing that and getting all this publicity about Chinook and stuff like that. And I said, why? What's such a big thing? She said, well, the two biggest media stories in the University of Alberta's history were this 1970 story and this 1978 story, and they're both bad news. So your story is a good news story. So thank you for knocking those two off the top of the pedestal. Now, in 1982, this innocuous paper came out written by this fellow named Ken Thompson, who I mentioned before. And if you know Ken, he hates writing, and so everything he does is minimalist. If he sends you an email, it's never more than one sentence. And usually words are omitted because they're unnecessary words. And he never uses a capital letter because that requires hitting the shift key, and that's extra work. So it's like minimal. So this was a long paper for Ken, and in it he ran an experiment that showed the more you searched, the better the program played. And if you extrapolate the results, he said, you know, if I got a machine that was maybe, you know, 1,000 times faster, my program would be the world chess champion. No knowledge, just search. The correlation between search and performance, speed and performance. Faster meant you could do more searching, you're going to look ahead further, you're going to play better chess. And this paper was devastating because it effectively ended a lot of work on computer games. There's Ken with the beard. He used this approach to build a chess machine with his colleague Joe Condon, which he called Bell. And Bell was all hardware, no software. Sorry. Yeah, there was some software that controlled it, but the whole chess engine was built in hardware so that it ran blindingly fast and could search incredibly deep with minimal knowledge. And it became the first program to get a master's rating. And that was recognized in 1983 at the ACM conference. And I was at the conference there competing with my program, Phoenix. And not only did he get an award from the chess community, you are the first master level chess program, but then over in the next meeting room in front of 1,000 people, the ACM gave him the Turing Award and his partner Dennis Ritchie, because Ken Thompson is the inventor of the Unix operating system. And so you all know Unix and its successor generations like Linux, but Ken became fascinated with chess and built a chess machine. In 1983, my new program, Phoenix, played in its first World Computer Chess Championship, and Tony Marsland's program, AIIDE, came second and third, so Alberta had a strong presence. And there's me in 1983. I had read Ken Thompson's paper, and I took it to heart, and I said, you know, Ken Thompson, he's using integrated circuits and putting chips together to build a machine. I can do better. I could build my own chips. And so that's a picture of me with 3 other students. And you can see in front of us the circuit diagram for a chess legal move generator that we built. And my first real research publication was in 1983, conference on VLSI, very large scale integrated circuits, the design and implementation of a chess move generation chip. Unfortunately, there's a sad ending to that story because we built the chip and we sent it off for fabrication, but there were problems with the fabrication process, and the chips did not come back to us until 2 years later, at which time I moved halfway across the country, and our team had been disbanded, and I still have the chips. If any of you want to play with them and see if they work, I would love to know it, but I'm actually very proud of the fact that the first chess chips we built, because of course, very soon after, other people did that as well, and they made theirs work. But this is an important lesson. You need to embrace your opportunities and pursue what you know is in the future. I had read Ken's paper. I knew where the future was. And this was the early days of, designing and creating your own chips. And that would give me another order of magnitude. And I just wanted to do exactly what Ken said, build something really fast. And that's what I tried to do, but never got to the finish line on it. In 1984, I went into academia, and my first job was to try and get research grants, and I was singularly unsuccessful. They were all turned down because I wanted to write computer games. And try as I might, I did not succeed because, as one grant application said, quote, computer games, work on something respectable. And it took me 13 years. It wasn't until 1997 that I got my first game grant. I didn't suffer as an academic because I wrote my grants then to be in parallel and distributed computing. And if you look at my publications, half of them are in parallel distributed computing because that's where I could get the money, and the other half were in games. And at least in Canada, it was a fight. Almost, 13 years, 15 years before that first tranche of money came to me that I could justify, the research agencies could justify giving me money to do something as esoteric as games. And I learned my lesson over that time. And so now my grants are all AI research using games as the experimental test bed. And you may say, well, that's obvious. But in 1984, it wasn't obvious. And I had to work to get to that. And so not just me, there are other people in the United States who had all of these same problems. So if you're getting grants to do AI in games, that hard work of educating granting agencies happened like almost 30 years ago. In chess, there was a weak grandmaster, which was came out in '86, a program called High-Tech, and it was, again, the first real demonstration of building your own chips. So they were 3 years later than me, but they built fully functional chips, and one chip wasn't enough. They used 64 of them in parallel, and the net result is Ken Thompson built Bell, one set of chips, pretty fast. High-Tech is 64 chips, all much faster, search much deeper. Voila, it's a stronger chess machine. And in 1986, I tied for first place with High-Tech in the World Computer Chess Championship. That was my dream. I was a chess player at the university, and I dreamed of being the world champion, and I realized I would never do that. I wasn't good enough. So I had this dream that one day maybe I would be the world computer chess champion, let my computer be the world champion. And in some sense, in 1986, I achieved that. And then along came this team, which was originally called Deep Thought. In 1987, they put a whole chess program onto a single chip, called it Deep Thought. And here's the team. And I want to point out this person here. This is Murray Campbell, who I met in 1974 in the Canadian Junior Championship. Murray was born here in Edmonton, did his bachelor's degree here at the University of Alberta, did his master's degree here at the University of Alberta, went to Carnegie Mellon, did his PhD, and joined forces with this fellow, Feng Shu, and built Deep Thought, which became Deep Blue. So there's an Alberta connection there. In 1989, the World Computer Chess Championships, Tony Marsland and I organized it here in Edmonton. And the winner was Deep Thought. And there's Feng Shu getting the trophy from Claude Shannon. And this was just held at the Convention Center, which is a couple blocks just east of the Chateau Lacombe Hotel, which many of you are probably staying at. During this time, there were many people who were looking at how to do optimization in chess programs. Optimization meaning parameter tuning. And there were lots of techniques that were proposed. We were privileged to have Michael Burrow in the audience here at the front row. He's a University of Alberta faculty member. He was also looking at these machine learning problems, how to tune parameters so that programs performed better. Michael, in 1997, his program Logistello for the disc flipping game of Othello or Reversi crushed the human world champion 6-0, and that was a milestone. But the chess people were looking at trying to learn how to tune these parameters. And in the 1950s and 60s, Arthur Samuel, working at IBM, wrote a checkers playing program. It was going to be chess, but it turned out that the 32 squares on a checkerboard were better matched for the hardware he was using than a 64-square chessboard. Nobody had 64-bit vectors back then. So Samuel had a checkers program, and he did the pioneering work in reinforcement learning to allow a system to automatically tune its performance based on playing itself. And in the 1990s, Jerry Tesaro's backgammon program, TD Gammon, demonstrated how powerful these ideas of reinforcement learning could be. This is a major contribution to well, AI as it exists today. By 1989, I was becoming disillusioned with computer chess. And I wrote an article with my friend Misha Donskoy. And let me just highlight one of the sentences here that I wrote, because the whole article is rather prescient. It says, after a decade of chasing the faster machine mirage, it now appears necessary to return to the basics, finding better search algorithms and better ways of using chess knowledge to solve the problem. Everybody piled into build it bigger and faster, because that's going to give you immediate returns. And guess what? We saw diminishing returns. Humans play chess really well, and going that last mile gets harder and harder the closer you got. And it wasn't a linear relationship. Like if you double the amount of speeds, you double the amount of gain in performance, and didn't work that way. And I'm pointing this out because people are just repeating the same mistake today. What's going on with LLMs? We need a bigger data center. We need 1,000, 10,000, 1,000,000 more GPUs, because we got to build a bigger model with not 1 trillion parameters. We need 2 trillion or 10 trillion parameters. Bigger is better. Well, it's diminishing returns. Do you think that ChatGPT or Gemini or Claude or any of these things is going to be twice as good because you have twice as many parameters? In the beginning, with a small number of parameters, there were lots of people who experimented with reinforcement learning and deep learning and other optimization techniques, and they had mixed results because there were too few parameters. But we crossed a tipping point where we got enough parameters and the performance was there. But now you're at the other side of this hill that we've climbed, where you're getting the diminishing returns, and you can't keep saying, I just need a bigger data center and more resources. Because eventually you're going to have to go back full circle and go back to the algorithms and the ideas and do it smarter, not taking a sledgehammer to the problem, doing it smarter. And I realized that in 1989 that my life had changed from Ken Thompson's paper, because all I was doing was trying to write software that ran faster. I take my program and I ran it on a network of workstations. In fact, there's an article out there that claims I was the first person to run an internationally distributed program, because my chess program could run on dozens of machines all around the world using over the internet. And I did it and it worked. It was so slow. God, those network speeds. Oh my God. Anyway, that's what I was doing. It's trying to make it faster. I pulled in all the connections to get supercomputers, right? And string them together, and I would tune the software. But who writes a paper about tuning your software to make it faster? I mean, that's not research. It's hacking. And so it came time to go back to the roots. And I was so disenchanted with chess that I switched. And in 89, I committed to checkers. And then a few years later, I also committed to poker because they opened up other research opportunities. And then what happened with chess? Well, deep thought gave rise to Deep Blue. And in 1996, there was an exhibition match. In 1996, Kasparov versus Deep Blue. Biology, Kasparov beat technology, Deep Blue 4-2. And in 1997, Kasparov lost to Deep Blue 3.5, 2.5. I was there for both of those. There's no question in 1997, Deep Blue was not the better player Kasparov was, but humans crack under pressure, and Kasparov cracked. He was the better player. But doesn't matter. The media said, oh, he got beaten. That's it. Chess is over. Whatever. There were multiple matches against other grandmasters, in particular Kasparov and Vladimir Kramnik, his successor world champion, played matches against strong programs and had trouble beating them. One of the things I'm proud of is that one of those matches, Kasparov versus Deep Jr. in 2003, I was a co-referee for the event, which is kind of cool to be center stage as the referee of a major international competition. And you get to meet Garry Kasparov, who's like an amazing person. And here's what's happened with chess. And it's not quite a linear curve, but you can see that there's been steady progress. You know, from the early 60s with very weak programs, and with Greenblatt's program coming up here, you know, through to Ken Thompson's program achieving master level, through to, you know, Deep Blue becoming, say, a weak grandmaster, through to, you know, the mid-2000s becoming the level of a world champion. And in 2005 was the last time a human defeated a strong chess program. In that game, the computer program was winning. It got into a strange position where there was a bug in the program, and the program lost, and the human won, and that was the last time humans won. And the progress, and you know, this is all part of this longest experiment in computer science history. We started getting the real data points here. We're still getting the data points here. And look at this chess rating. The human world champion, the best player in the world, Magnus Carlsen, is in the rating of about 2,800. The best programs now are about 3,600, which means in a match, the human would get obliterated. In fact, at speed chess now, or blitz speed chess, computers can give humans the odds of a full knight. A knight is a big piece. The computer will play the humans, the best humans in the world, without a knight, and consistently beat the best humans. The gap is so huge, and this is still growing. And now the movement is not about who cares about better. We've beaten the humans, who cares about it? The quest is now to try and solve chess. Chess is 10 to the 45th. I solved checkers, which is 10 to the 20th. That's a lot. Somebody said, oh, 10 to the 20th, to 10 to the 45th, all you have to do is double the computing. It doesn't work like that. So anyway, chess programs are just amazing. It's rather humbling. But stuff with chess hasn't quite died, because there's still interesting things happening. In the early 2000s, the invention of using Monte Carlo search, Monte Carlo tree search as it's now called, and that is to replace human knowledge altogether with statistics. As you search, gather statistics. Hey, if I do a deep search and I find that if I play this move, I seem to win 55% of the time, and if I play this move, I seem to win about 32% of the time, I don't know which is the better move is, but based on statistics gathered from search, this wins more often than this, so I'm going to play this move. Just use statistics. It works incredibly well. And University of Alberta professor Csaba Szapaszfari, with his UCT algorithm, was one of the pioneers in doing this work. And then we get up to 2016, where perhaps the last word on computer chess programs with the AlphaGo, AlphaZero, and Mu0 programs. Here's the 2016 match between Google DeepMind, actually it was DeepMind's program then called AlphaGo to play Go against perhaps the greatest human Go player of all time, Lee Sedol. There's Lee Sedol with his daughter, shaking hands with the CEO of DeepMind, Demis Hassabis, who is a passionate games player and was a chess prodigy. And the AlphaGo defeated Lee Sedol. And of course, many of you may have heard of Demis about a year ago. He won the Nobel Prize because he and his team at DeepMind developed AlphaFold, which does protein folding. And for that, he got his Nobel Prize. And in this program, which goes from AlphaGo had a lot of human knowledge, AlphaZero had no human knowledge, MuZero didn't even know the rules of the game. And so MuZero is an incredible program because it plays multiple board games, including chess, and it starts off without even knowing the games, the rules. It just plays a game, and of course, it makes lots of mistakes in the beginning, but it starts to learn what legal moves are, and from that, it learns and builds this with deep reinforcement learning, builds these networks, and eventually plays world-class chess. And with a massive supporting computing infrastructure, 1,000 or more processors behind, it learns to play superhuman chess in 4 hours. Humans spend a lifetime learning to play chess, and this program goes from 0 to superhuman in 4 hours. A few things to note. The architect, lead author on the multitude of science and nature papers that came out was David Silver. David Silver did his PhD here at the University of Alberta and a postdoc here at the University of Alberta before joining Demis Hassabis, who he worked with at a games company before coming to Alberta to do his PhD. And obviously it worked for David because he has 270,000 citations. 270,000! That's like 20 times as many as I have. And I was pretty proud with like 14 or 15,000 citations, okay? But 270, and never mind. Okay. No, I'm not jealous. I'm not jealous at all. Not at all. But of course, he was passionate about Go, and he came here and he learned reinforcement learning and Monte Carlo tree search and did a fantastic PhD and went to DeepMind and led the effort to build AlphaGo. And core technology there was not just deep learning, but also the use of reinforcement learning. Demis Hassabis formed DeepMind because he believed in reinforcement learning. And although Arthur Samuel laid the groundwork in the 1950s and 60s, Rich Sutton did the hard work of formalizing the algorithms and turning them to powerful tools in the 80s, 90s, and early 2000s. And Rich Sutton is a faculty member here. He's been here since 2003, so 22 years. He's the father of reinforcement learning, and earlier this year, Rich Sutton deservedly won the Turing Award. So, sorry, I'm 9:59. That clock is wrong, and it doesn't move. Okay, so I'm a few minutes late. I'm going to have to hurry. What I want to point out is large language models. They're doing massive computing, but massive computing, game AI played a leadership role in the 70s and 90s, and were the first large-scale computations in the AI field, opened the door to the realization you could use massive computing to solve problems. There were massive data sets, and I'd like to point out, the checkers work that I did in the 1990s, which built a 250 gigabyte data set, which was massive for the 1990s. At $5,000 a gigabyte, that was a very expensive database to build. And I also did it with single agent search, building giant tables. My first paper on technique called pattern databases was rejected from AAAI because I built a 1 gigabyte database. And I got back the referee report saying, 1 gigabyte, that's ridiculous. Nobody will ever have gigabyte databases. So I was slapped down, and I'm still bitter about that. And then, of course, there were deep learning, and what Joshua Bengio, Jeff Hinton, and Jan LeCun did with deep learning got them the Turing Award. And they're also using reinforcement learning, which Rich Sutton is the pioneer for. So deep learning really has nothing to do with the University of Alberta or games, but the massive computing, the massive data, and the reinforcement learning all have ties to the computer games industry and or the University of Alberta. Some of the games related contributions that I want to brag about for what we did in AI in games is the computer chess was milestones in computing science and AI, and the Deep Blue and the AlphaGo matches are still today the two biggest media events for the field of AI. Games and computer chess in particular pioneered competitions, annual competitions. They also pioneered automated self-play. There are a variety of algorithms for efficient high-performance search. Many ideas that were pioneered in computer chess have worked their way into fundamental search algorithms, and people forget that these ideas came from the computer chess community. The notion of equivalence of search is knowledge, that search can compensate for knowledge is fundamental, and it came from computer chess. And there are many seminal results in and applications of machine learning, particularly reinforcement learning, that came through games and chess. And for me, although I started in chess, I moved on to many other interesting projects in checkers. We became the human world champion in 1994, and in fact, we solved the game in 2007. I then worked on achieving superhuman poker play through to 2008, and then my colleague Michael Bowling at the University of Alberta here took it further and solved two-player poker. And then I moved into biotools, which is bioinformatics. I really didn't have much interest in bioinformatics, but it turned out some of the checkers technology was actually fundamental to doing large-scale bioinformatics. And so it was kind of cool to have a commercial program that sold quite well that was doing biological analysis with a checkers engine inside, which is bizarre. And then I was working on video games with Bioware and Electronic Arts for many years, and some of our pathfinding algorithms ended up in commercial computer games. In 2014, my second company, Onlea, which still is up and running today, does online learning. And as of 14 days ago, I've started a new company which does private large language models. So I want to point out the bitter result. I now realize with perspective that a lot of my research is now obsolete, because like I did it, it was state of the art then, but it's been superseded by a bunch of newer stuff. And that's actually a sobering thought to think that I did all that work and now nobody cares. You should care. I poured my heart and soul into it. I could give you copies of all these great papers. Well, no one's ever going to cite them anymore because, like, there's better things. Oh, sigh. And to be candid, I wrote papers about the alpha beta search algorithm, and you'll find it in every AI textbook. But quite frankly, the whole history of alpha beta search should almost be a footnote in the history of AI now, because again, it's being superseded by other things, and things evolve. And in many ways, some of the things that I did and my colleagues, Michael, for example, have helped make our research obsolete by replacing it with newer and better ideas. One of the things that is interesting to me, and I don't think gets enough attention, is that game AI has foreshadowed much of what AI is today. Large-scale computations started with games like chess. Building special-purpose chips started with chess. Building large databases and repositories started with chess. games using to tune parameters and practical applications started with a lot with games. And so we in the game AI community need to take a lot of credit for many of these things. So for me, being early meant I missed out on a lot of things. Sometimes it was because I didn't have the computing resources. Sometimes I didn't have the data resources. Always I had a lack of money. I never had a lack of vision, of course, but then there were other people who got in my way who had a lack of vision. Oh, who would ever think of using a gigabyte for data? I want to shoot that. No, so I want to talk to that person. Anyway, he set back my career because that was a great paper. And it would have been on my annual report. I would have got an extra increment and I'd be richer than it was. Never mind. Okay. Anyway, the lesson here is if you have a good idea, pursue it in any way possible. Don't let those obstacles get in the way. And I think everybody in this room has a great opportunity because the computer games industry is reinventing itself. LLMs have changed the playing field. We're in quicksand right now because everything is shifting. How games are designed, even the types of games are changing because of LLMs, and they're changing because LLMs are going to help us build these games faster, better, in different ways. And so I think there's just incredibly ripe time to do all sorts of innovative things. And if you're not thinking about how the world is changing, then you're not leading edge. And research is only exciting when you're leading edge and when you have impact. Impact could be lots of citations, and it could be spin-off companies, and it could be awards, whatever. But don't get stuck doing minor incremental things. Think big, use your imagination. This is the best time to be in the computer games industry because so much is happening now, and you have an opportunity to take a leadership position. And so I'm going to conclude quickly because I'm over. These are some of my opinions. Take it for what it's worth, and I'm happy to argue them. AI can fool most of the people most of the time. In many ways, I say AI is a real con job because I don't believe that there's anything out there that is intelligence. It really goes to the next point that my mantra with AI is it's the result that counts, not how you get it. We are magicians. We're Harry Houdinis or David Copperfield. We create this illusion, and when you look under the covers how these programs work, they're not intelligent, but they achieve the results, and that's fine. So I like to say that what we do in AI is we create the illusion of intelligence, and that's the best exemplified by large language models. They create the illusion of intelligence. I just read an article this week that said, no, they're not creating the illusions of intelligence. We have made a mistake. We've defined the word intelligence wrong. We have to change the definition of intelligence. And once we've done that, then of course LLMs will be intelligent. What a non-intelligent argument that is, but okay. LLMs are a major advance in AI language and reasoning capabilities. Fantastic. It is a big step forward. But people are saying that they're AGI, artificial general intelligence. They are not. They are raising the bar, performance bar, but they can't lead. The algorithms fundamentally cannot lead to an AGI solution. So all this talk about AGI is crap. Sorry. All right. I have to be careful on that. You know, now that I'm retired from academia, maybe I'm using too many words that I shouldn't be using. But okay. I also want to say that deep learning is a major advance in AI optimization. Great idea, but it's not the answer to AGI either. But I know one thing. Whatever AGI is, reinforcement learning will be part of a learning system. It's fundamental. And so the only technology I see today in the machine learning and AI sphere where things are going on that match my metric of what I think is going to be in an intelligent machine is reinforcement learning. And so I find that to be the most interesting and productive and important area of AI research today. Anyway, thank you very much. And I'd love to be critiqued and given a hard time about some of these opinions and comments. And thank you for the opportunity to speak here today, and I hope you all have a great conference. Thank you very much.